of the fancier sorting algorithms that we're going to take a look at is called merge sort. It's a very well-known one. It was created back in 1948. A computer scientist slash mathematician and all-around smart guy named Jonathan Van Neumann wrote the first ever recorded program of merge sort. It was 23 pages of code for this computer here called EDVAC. It's a very large computer. It was like 6,000 or so vacuum tubes. Writing code back then, obviously very different than it was today, but the algorithm, the idea, was first conceived in 1948. So the idea behind it, it's really a combination of two things, merging and sorting. And actually, you could say it's really a combination of three things. Splitting up, sorting, and merging. All three things take place. So it exploits the fact that arrays of 0 or 1 element are already sorted. So if you were asked to sort an array that just consists of the number 1, and that's it, you know it's sorted. Or it's just number 9, it's sorted. Or if it's empty, it's sorted. So merge sort takes advantage of that fact. It works by decomposing an array into smaller arrays. So that's something known as a divide and conquer algorithm, a divide and conquer approach. We split up the larger array we're trying to sort into smaller sub-arrays. All the way down, we keep doing it until we get to 0 or 1 element arrays. So we would take an 8 element array and split it, and then split it, and then split it until we end up with 8 single element arrays, and then we merge them back together. So here's a little visualization. Imagine we have this array here, 8, 3, 5, 4, 7, 6, 1, 2. That is 8 elements. What do? We start, or the code starts, by splitting it in half. So we're dividing it. We're still not at 1 or 0 element arrays, right? These are 4 elements, so we split again. And now we have 4 2-element arrays. We're still not there, so we split again. Now what we have are 8 single element arrays. So now we merge them together. So let's focus here. We take these two arrays and we merge them back. And as we merge them, they are already sorted. We know that they're sorted. So merging two sorted arrays is easy relative to merging two unsorted arrays. So what we do, we basically just compare the number. Which one is smaller? Well, the smaller one goes first. Which one of these is smaller? The smaller one goes first. Which one of these is smaller? Put that first. 1 goes before 2. Then we repeat the process. Now we're merging this array with this array. But notice, this is already sorted, this is already sorted. So now we just make a couple comparisons. Take the first item, compare it to the first item. Which one is smaller? Put that one first. Then we take this item, compare it to that item, which is smaller. Okay, put 4, and then we do it again, put 5, and then 8. And then the same thing over here. So we end up with 1, 2, 6, 7, and 3, 4, 5, 8. 2 sorted arrays that are smaller. Now, our final merge, we put them all together. And we end up with this 1, 2, 3, 4, 5, 6, 7, 8. So hopefully you can see, yes, this algorithm is a little more complicated, but it involves first splitting up until we end up with sorted arrays, which are 0 or 1 element. That's the base case, that's the smallest thing we get to. We know they're sorted if they're only 1 item long or they're empty. Then what do? We merge them. Merging sorted arrays is easy. Well, compared to merging unsorted arrays. Still not that easy. And we sort them back until we finish and we get a totally sorted array. Here's another visualization. Here we have 8 elements in an array, and the very first thing that happens is we split them all up into 8 individual arrays. So now they all have, each color represents the fact that they're an individual array. And then you'll see as we merge them together, they change color. So it starts with the first 2. These are 2 arrays. How do we sort them into 1? 3 and 44. Takes them out and puts them back in that order. They're sorted. So now we have, this is 1 array here. So we have 7 arrays, right? Oh wait, 1, 2, 3, 4, 5. Yes, 7, I can't count. So next, we take these 2 individual arrays and we sort them into 1 and put them back. Now, we take these 2 arrays, the orange and the red, of those 2 items each, and we sort them into 1 array, like this, and then we put that back. Then we have to start on the right side. So this was the left division. Now we take 47 and 15, we sort them from 2 arrays of 1 item into 1 array of 2 items. Same thing with 36 and 26. Now what do? We merge these 2 arrays together, the yellow and the green. There we go. Put that back in. And now we merge our two arrays of 4 items at the very end. There we go. So that's merge sort. And as you can imagine, there's a little bit of logic involved. In the next video, we're going to implement the first step, which is merging. So we have to understand how to merge 2 sorted arrays, and then the rest is actually pretty easy. So in the next video, we're going to cover that. We're going to build a merging function. Hey again, welcome back. So this is the first part of writing merge sort, which is writing a function to merge 2 sorted arrays. So again, we assume the arrays are sorted, and all you have to do is return the combination of those 2 sorted arrays. So for example, I already have it written here. Well, I'm not showing you the code, but I have the function call here. 2 sorted arrays, 1, 10, 50, that's sorted. 2, 14, 99, 100, that's sorted. When I run this, I merge them together, we get 1, 2, 10, 14, 50, 99, 100. So 1 array that is returned. So that's basically your job. If you want to try and do this on your own, I'll have a solution in the next video. This part's, well, personally, I always hate saying something's hard or easy, but I think the logic for this one makes sense. So we'll walk through it, though. I have pseudocode. So I jumped the gun on my slides. Yes, it's useful to first implement a function responsible for merging 2 sorted arrays. Given 2 sorted arrays, the helper function should create a new one, which is also sorted. And yeah, it's important. It needs to consist of all the elements in the 2 input arrays. So what do we do if they're not the same size? We'll cover that. And as far as how it should work, this is something we haven't seen, but it should run in O of n plus m time and O of n plus m space. So n and m, we have 2 inputs now to our function. 1 array and then the second array. So n is the size of the first one, m is the size of the second one. Of course, those are 2 that sound very similar, and you probably can't tell when I'm saying n and m, but that's the standard way of saying it, of writing it down. So that just means that if n grows super large but m doesn't grow very large, it should just be O of n plus m. Often, and usually in merge sort, they are the exact same size or 1 element different in real life. But if we're working with something and for some reason we're merging an array of 1,000 items with an array of 1,000,000 items, it should be O of n plus m. So as that 1 grows, anyway, all I'm saying is that you should visit each item in the array 1 time. Right? If it was just O of n, that means that it's linear time. You visit each item once, you iterate over it. But if it's O of n plus m, that means that we're iterating over each item in each array once. So here's the pseudocode. Create an empty array. So define a function, takes 2 inputs. Create an empty array that you'll return at the end. And then you start with the smallest values in each input array. You start at the beginning. So have 2 counters. One called I, one called j. I recommend using while loops for this. Personally, that's what I like to do. And you need to have one that starts out, they both need to start at 0. J and I are 2 numbers, start at 0. While there are still values we haven't looked at, meaning while I and j both haven't hit the end of their respective arrays, we're going to take the value of the first array, of the first item, and then compare that to the value of the first item in the second array. Now, if the first item is smaller, we put that in our result array. And then we move on to the next item in the first array. If it's the other way around, if the first array is larger, the item in the first array, then the value in our second array, we take the value from the second array and put that in the results and move on to the next value in the second array. And then once we finish one array, we just push all the remaining values from the other array in. So, for example, if we took these 2, I'll just write them down here. These are our 2 arrays, and then this is my result that I'm going to return. We start with 2 counters, I and j, and they start at 0 and 0. So we compare 1 and 2. Which one is small? 1 is. So we put 1 here. And then we move on. In this first array, we're now looking at 10. So if I were to put a little marker here, like that, it's not a very great way of writing that, and our marker over here, this is going to bite me, this is going to be annoying to keep track of, is 2. So next time through, we're comparing 10 and 2. Which one is smaller? 2. So we put 2 in here, which means that now we need to shift this over, and now we're looking at 10 and 14. So now which one is smaller? 10 is. So we put 10 in, and then we move this up, not this one. Now we're looking at 14 and 50. Which one is smaller? 14. All right, so then we move this to 99. Get out of there. Okay, 50 and 99, which wins? 50 wins. So then we've now exhausted that array. that tells us, if we've hit the end of this, all we do is take all remaining values in this other one, because if this is sorted, and they have to be sorted in the same way, I should have mentioned that. We can't have one in ascending and one in descending. They're sorted in the same way. Whatever is at the end of this array, if we have stuff that's left in the other array, we know for sure it's all greater than whatever, that 50 in this case. So now we just add in 99 and then 100. And now we have successfully merged the two arrays. So that's the approach that I'd like for you to try and take. Otherwise, if you don't want to do it, in the next video, I'll just show you a solution. So this is a first important step for merge sort. All right, welcome back. Now let's write the code to make this work, to merge two sorted arrays. So if you jumped this video because you saw implementation in the title, I recommend you just go back and take a look at the rough pseudocode, how it's supposed to work, just so you understand what we're doing here. So here, I'll start by defining, I have a snippet as always. I'll call it merge, my function, and it takes in two arrays. Let's just do ARR1 and ARR2. And then here, the very first thing we should make is just make a variable called results. Empty array, and then at the very end, we return results. Like that. And then we need to do all of our logic. So the first thing we'll do is make our two little pointers. We're going to start with a variable at 0 and another one at 0, one for each array, and then they'll move through individually. So we'll do let I equal 0, let j equal 0, or whatever. You could call it ARR1 index or something, but I'm just going to go with I. Okay, so now the bulk of our logic, we need to have a while loop that runs while I is less than the length of the array and j is less than the length. Basically meaning while there is still data for us to look at in both. If we hit the end of one of them, remember in the last video that I showed, when we started here, then we hit the end of 50, and there was still data here, we're going to do something else. So this first loop only applies when we're looping through both at the same time. So while I is less than array1.length, and j is less than array2.length. Perfect. Now we just do a simple comparison of array2 of j and array1 of I. So it's up to us which one we want to do first. So I'm going to say if array2 of j is greater than array1 of I. It's so confusing to try and talk about. If this is our results, we're basically checking if this one is greater than this one, what do? We take this and we put it in results. So if that's the case, we're going to say results.push array. Oh, and I said that backwards, I'm sorry. If this one is greater than this, then we take the smaller one and we put it in there. I don't know why. We're not trying to do descending order. We want the smallest items first. All right, so we're going to push array1 of I if it is smaller, if array1 is the smallest thing. And if that's the case, if we actually push array1 in, we then need to move I is no longer going to be 0. We need to move I up by 1. And that's super easy. I plus plus. Okay, so now we have an else, which is a lot of times, well, I guess we haven't covered the edge case if they're the same value. So instead of doing an else if array2 is less than array1, because if we just did greater than and less than, we'd be missing the case of equality. But we can just pick one. We can do greater than or equal to with an else, or do greater than and then have an else which will catch the case when they're equal and when array1 is greater. Okay, so if that's the case, otherwise we do results.push array2 of j, and then we increment j by 1 because now we're moving up. So that would be do we have that scenario? Let's see, the first time through, we put 1 in here, and then we're looking at 10 and 2. Yes, so now 2 is smaller. So in that case, we add 2 in, which is from array of j, but then we increment j by 1, and we go here. Array of 2, I mean. All right, so if we look at what happens at the end of this loop, let's print this out. Well, we're going to return results, so we don't actually need to print it. It's not complete, but it's getting there. So we end up with 1, 2, 10, 14, and 50. Because what happened is we did this, then this. We did 10, 14, did 50, and then we hit the end. Because we did 50, and then we added 1 to I, and we hit the end of the array. So this loop broke out. We finished. So what needs to happen afterwards, once we exhaust one of them, because remember our condition, while I is less than array1.length and j is less than array2.length, once we hit the end, we then just take everything that's left in j and add it in. Or if this was shorter, like here, if we hit the end, we then take whatever's left in the first array and add it in. So that's easy as well. I'm just going to do 2 while loops, and I'll just have a while loop while I is less than array1.length. What are we going to do? Results.push array1 of I, and then just add 1 to I. So basically the same logic in here, it's just that we're not doing a conditional check anymore. And I'm going to just duplicate this, but then replace I with j, and array1 with array2. Does that make sense? So whatever happens at the end, we merge them as far as we can until we hit the end of one of the arrays. So let's say we hit the end of array 1. That means that array 2 still has stuff in it, so j hasn't hit the end. So j will be less than array2.length. In our case, if we hit the end, 0, 1, 2, 3, we get 1, 2, 10, 14, 50. That means that j is currently at index of, 0, 1, 2. So we have to add this in, and we have to add this in. And then j will have hit the end. J will be equal to array.length at that point, and then we finish. And we return results. Let's see if it works. That looks good. If we try something sneakier, like an empty array, and then the array 1, 3, it still works, because this loop never runs, right? All that happens is that we have array of 2, so j is less than array of 2, so we just push in all the results, or all the items in array of 2 into results, and then return that. If we tried, let's see, doing something like 100, and then over here, I don't know, I don't really even have anything worth showing at this point. That won't work, it needs to be sorted. All I want to show is that it works, and it does. Okay, so this is the first part of merge sort. This is the longest part, actually. If you came up with something better, definitely share it in the comments, post on the discussion board. But this is a pretty simple way of doing it, and I think it's pretty legible, pretty easy to understand and walk through. So we're going to use this code in the next video where we add on and actually implement merge sort. Right now, this only works with 2 sorted arrays. Okay, see you then. Hey, welcome back. So now we get to the sorting part of merge sort. And this is, actually the code itself is pretty short. It's only, my solution is, 5-ish lines. The problem is that conceptually, it's a bit hard to understand. And that's because most merge sort implementations use recursion. So if you skip the recursion section, I highly recommend you go take a look at that, because this is going to seem a little insane if you've never seen recursion before. And even if you have, it's not immediately intuitive to write code that's recursive. So here's how it works. We have our merge function that works. We just assume it works at this point. If you didn't write it, just go to the last video, copy the code if you want to try and implement this yourself. But again, don't feel bad if you can't. This is really about the concept, how it works, not about you being able to write it from scratch immediately. Okay, so merge sort. We have our merge function takes 2 sorted arrays. Now remember, the goal is to basically keep breaking up the array into halves. So how do we break an array, just a single array, into a half, 2 halves? Think about that. My recommendation is to use slice. So array.slice, and you go from 0 until the middle of the array, and then you go from the middle array until 0, and that gives you 2 halves. And then what are you going to do with each one of those halves? Well, you're going to call merge sort again, and you're going to break each half into its own halves, and keep going recursively. And what's our base case? When the arrays, their length is less than or equal to 1, meaning that it's 1 or 0. Okay, so that breaks them all up into these small elements, these small arrays, using slice recursively until, again, our base case is we hit the end. Array.length is less than or equal to 1. Then, once we have those small arrays, we merge them back using our merge function that we've already written until we're back at the full length of the array. Now, it seems simple when you write it this way, but the code, it gets confusing when you're writing it recursively. Let's put it that way. But that's pretty much it. So once the array has been merged back together, we return the merged array at the very end. Okay, so if you want to take a stab at this, definitely do it. But in the next video, I'll walk through it. Remember, recursion is kind of crazy. It can be a bit of a leap to get there. So So don't feel bad if you can't get this one. Okay, see you in the next video. Okay, so let's get writing our own merge sort. So I have a new snippet again. I have our merge function that works from 2 videos ago. We can get rid of this line for now. Now I'll define our merged sort function, which takes a single array. And if we go back to our pseudocode, all that we want to do is keep splitting it up into smaller arrays and calling merge sort on those arrays until the length of the array is 1 or 0. So we can start with the base case if we want. If array.length is less than or equal to 1, we're going to return the array. Not array 1, array. So right now, it doesn't mean much, and basically we're not doing any recursive calls. Remember, every recursive function has a base case and then the recursive case, the recursive function call. So we're going to call merge sort on something again. But it needs to be on the 2 halves of the array. So how do we split this array in half? So for example, if I call merge sort down here, array 10, 24, 76, 73, 72, and 1. So how do we split this in half? If we just took this, I recommend using slice. So if I say this variable var arr equals that, how do we slice it in half? Well, we go from 0 to the left side. We go from 0 until what? How do we find the midpoint? Well, we can take the array length divided by 2 and floor that. Alright, so remember binary search, we did the same thing. So that's what I would do. I do math.floor of array.length divided by 2. And that gives us 3. So then I would do array.slice from 0 to 3. And that gives us the first 3 items. And then we need to do array.slice from 3 to what? We do that actually just do array.slice 3. And it will go from 3 until the end. That's how it works. You don't have to pass in the second number. So that was the array. That's our first step. And we'll call merge sort on each of those. So let's just write that code start. So we can define the midpoint here. So let midpoint, let's just call mid, equal, or just the same thing we saw, array.length divided by 2. So that gives us halfway point. Then we're going to say the left side equals array.slice from 0 until the midpoint. And then we'll say the right side equals what? The right side is going to be array.slice just from midpoint until the end. So now we've split that array into 2 pieces. This is R here. There we go. Now comes the tricky part. Instead of just doing left equals array.slice, I'm actually going to call merge sort array.slice. And the same thing here, merge sort array.slice until the end. Okay, so what's happening here? We call this the first time through this array. Array.length is not less than or equal to 1, so we skip that. We find the midpoint. We find left and right. So if we focus on left, we're calling merge sort again on this array. So that goes through, and it's called again. Array.length is not less than or equal to 1, so we skip that line. Then we split it in half again, and now we call merge sort on the left and right. And then one time through, one of them has the length of 1. So we return that array. The other one is length of 2. Because there's 2 numbers. So we call merge sort again. And then that one we have 3 single item arrays. And now we have to worry about merging them back. And this is the third bit of magic. We merge the left and the right. So this is the code. I'm going to walk through line by line how it works. We're going to step through the call stack with a small version, but let's just make sure that it's working. So if I execute it, 1, 9, 10, 24, 72, 73, 76. Okay, now let's call it on, let's do 4 items. And I'm going to put a breakpoint right here. Now if we look at what happens just with these 4 items, I'm going to step through it, so I'm going to run the code. And I'm going to close the console with more space. Look at our call stack over here. Okay, here we go on our journey. we start and merge sort is called on this array. It's 4 items long, so this first thing does not happen. Then we find the midpoint, which is 2. Now here's the first thing. Watch what happens to our call stack. We are recursively adding, so there's another merge sort that's going to add to the call stack. If you look now at this merge sort, it's going to call on that left half, right? The left half is just 10 and 24. Is the array out length less than or equal to 1? No. So we skip it. And what happens again? We find the new midpoint, which is just index, which is just the middle of this array. We're calling merge sort on what? We look at our stack again. There we go. Calling merge sort on a single element. 10. Alright, now, this time array.length is less than or equal to 1, right? So we're going to return the array of 10. And you'll see it pop off the stack here. Just a second. Return value, array, and it pops. Next, we're back to this one. So now we're back to, we left off right here, right? This is a hard thing about recursion. I wish I had a whiteboard diagram this all out. But we were waiting. This function call waited for left to go all the way until it returned something. And now right needs to go all the way until it returns something. So right on that second half is 10, 24. We split it, and the right side goes in, and we get the array of 24. Array.length is less than or equal to 1. So we return array, and you'll see it pops off the call stack in just a second. Now, we merge the left and right, 10 and 24. And when we merge them together, it calls merge. All this code happens, and at the end of the day, we end up merging, and then finally returning. And watch the call stack. Now we pop off again. Now this time, we finished left. Right? That was waiting. In this code, we were waiting to merge the left side. Now we need to do the right side. We never even ran this line. So now the right side is now going to go. And if we take a look, it's calling merge sort again with, where's it passing in? Just a moment. There we go, 76 and 73. So array.length is not less than or equal to 1, so we didn't return it, so we move on. Now we call merge sort on the left side, which gives us 76. The array.length is less than or equal to 1, so we're going to return array, and you'll see it pop off that call stack. Keep going, there we go. Now we're back here at merge sort for the right side. It's crazy, I know this is a hard part to understand, but we're back here, and this time we're calling it a 73, array.length less than or equal to 1. That's true. We return that array, which is 73, pops off the call stack. Now what we have is left and right. So left is 76, right is the array 73. We merge them together, so we call back up here, go through this, merge them, and then eventually we return the results, which is the merged array. Now we return that from this merge sort call to our original call of merge sort, which was waiting. So we have left and right that have now been merged. Well, they have been merged together. So they have been sorted, split up and sorted individually, and then merged. Now we have two arrays that are 2 items long, and we merge those together with our final merge, left and right. Now this code takes a bit longer because we've got 2 pieces of data for each one. You can see results down here. We return results to merge sort. So now we have 10, 24, 76, 73, and that is what we return out. And finally, if I show the console, we end up with that return value. Whew. So as you can see, it's a lot to keep track of in Node. Just 4 elements, trying to keep track of it all in your head can be a lot. So I diagrammed it out, and let's just take a look at the actual order things happening. So when we call merge sort on 10, 24, 76, 73, first thing that happens, array is this array. We check, is the length less than or equal to 1? No. So we find the middle point, and then we call merge sort on the left side from 0 until the midpoint. So this is called merge sort of 10, 24. So then in that code, if our list is 10, 24, it's still not less than or equal to 1, the length. So then we call merge sort again on the left. And now, this time, the length of this array is less than or equal to 1. And in that event, we return array. So we return 10. Now this merge sort of 10, 24, the list of 2 items long, it now has a value for left. So next, it finds a value for right. It was waiting for this to come back, remember. Now it came back, so it moves on to the next line, right. So now we call merge sort of the right side, which is 24. Merge sort of 24, the length of that array is less than or equal to 1, so it returns 24. So now we have our left and we have our right. So now we can move on to this line, merge left, comma right. So when we call merge left, comma right with 10 and 24, remember our merge function takes the 2 sorted arrays, it merges them, and that returns a value, which is the array 10, 24. Yes, it was already sorted, but ignore that part. Our code doesn't know that. So it returns a value now. So that was returned from this merge sort call, which was the left side of our first merge sort. So now our very first merge sort was waiting, and it has a left side returned. Now it's going to do the whole right side. So we call merge sort of 76, 73. In that code, the length is not less than or equal to 1, so it computes the midpoint, and then it does the left side, merge sort of 76, which that is a 1 item array, so it returns the value 76. Then this right side, which was waiting, we completed this side, now we're going to merge sort the rest. And that gives us 73 as a return value, because it's a single item array. Then, once again, we move on to this line. This was waiting, merge left and right. Well, now we have our left and our right, so we merge them, and that returns 73, 76, 2 item array. Then, this merge sort up here now has the left and the right that it was waiting on. So it finally, we got this, then eventually this, now it can actually merge left and right. And to do the left and right merge, we end up with this, 10, 24, 73, and 76. I know it's a lot, but remember, I've said this a couple times, just focus on being able to explain what's happening or walk through. If you have a whiteboard or a piece of paper, it can be really helpful to write down exactly what's in the callback at any given point. And I recommend you don't try it on a super long array. If you go into like 6, 7 items, it takes a lot more time and a lot more space to diagram. Please don't feel too intimidated by this. In the next video, we'll talk about the big O of merge sort. Alright, welcome back. I just want to quickly talk about big O, time and space complexity for merge sort. So we haven't mentioned it really, although I showed you in the very first intro to merge sort video how much faster it is, at least anecdotally, compared to something like bubble sort. But the best case, the average case, and the worst case for merge sort are all the same, O of n log n. So unlike something like bubble sort did okay. It was, well, I wouldn't even say okay. It does pretty poorly. It's quadratic and square time. Unless the data, in the best case, is already sorted, in which case it improved to linear time, O of n. Merge sort has no such, I don't want to say this. There's no edge case like that in merge sort. It doesn't care what the data looks like. It doesn't have an impact. It's going to split it up over and over and over and merge things over and over and over, no matter what the input is. If it's already sorted or if it's reversed or totally random, it doesn't really matter. So that's the first point. Now the second thing is, why is it n log n? Where does that come from? And definitely I would not expect you just to know that or even necessarily to be able to compute that right away. But here's a basic overview. So if we start with an array of 8 elements, so this is showing at the end of the process of merging them together, but let's say we're starting here and moving upwards. So we have to split it into 2 pieces. So that's one decomposition. Then we split it again, and that's another decomposition, and then again until we get items that are arrays that are 1 item long. So what's the relationship here? If we have 8 items in the array, n is 8, how many times do we have to split in order to get single element arrays? In this case, it's 3. But if instead we had an array of 32 items, I'm not going to type it all out, but imagine that I'm just writing the length here. So we have an array of 32 items. We can do a split, which gives us one array of 16 and another of 16. And then we can split that again, which is what would happen. We get 8, 8, 8, 8, so 4 8-item arrays. And then we split that again. And what do we get? We get 8 4-item arrays. And then we keep going. And I'm not going to count these precisely. It doesn't exactly matter anyway if I get the number right. The point is, though, eventually we're going to end up with 32 1-item arrays. Now, how many splits did we have to do to get there? I'm not counting. Please don't hold me accountable later. How many splits? Well, here's the first split, the second, the third, the fourth, the fifth. So as n grew to 32, we had 5 splits. When n was 8, we had 3 splits. What's that relationship? Well, going back to the big O section, that's log n. Now remember, we're talking about base 2, so log base 2 of n. What that really means is 2 of what power gives us n. So in our case, if we have 8 elements, we take 2 and raise it 3 times, 1, 2, 3, to get 8. Or if we have 32 elements, that means 2 times 2 times 2 times 2 times 2. 2 to the 5th power is going to give us 32. So that's where the log n comes from. As n grows, the length of this array, the number of times you have to split it up grows at the rate of log n. Now what about the n log n? Where does that come into play? Well, each time that we decompose it, we have O of n comparisons when we're doing the merge. So for example, let's take a look at this row right here. This is on the way back to the merge towards the last step of merging. There's always 8 items we're comparing each time through, right? We're not adding or removing items at any point. We're just splitting them up and moving them around. There's always 8 things total. So here, we would start and compare 1 and 3. That's a single comparison. And then one of those is chosen, which is 1. So then we move on and we compare 2 and 3. And then we compare 3 and 6, and then 4 and 6. And at the end of the day, we have O and N comparisons on each of these. So as the length of n grows, the merge algorithm itself, not the merge sort, just the merge, has time complexity of O of n. So if we have 1,000 items in the array, there's roughly 1,000 comparisons that need to be made. If we have 8 items in the array, there's roughly 8 comparisons that need to be made to merge. So in total, we end up with n log n. So O of log n is the number of decompositions. As n grows, there are the number of times we split n, the number of times we split the array grows at the rate of log n. But then each time we do split each decomposition, we have O of n comparison to actually perform the merging. So in total, we end up with O of n log n. So if we look at a chart, here's O of n log n. You can see it's way better than something like O of n squared quadratic time. It's not as good as O of log n, of course, or linear time O of n, but this is actually the best that we can get for a sorting algorithm. Unless the algorithm itself takes advantage of some weird quirk in the data. So there's an algorithm we'll look at called radix sort that uses a particular quirk of numbers, and it won't work to sort anything else. But if we want a data agnostic sorting algorithm, the best we can do is O of n log n. So merge sort is doing great. It's always O of n log n. Best, worst, and average time. And then finally, space complexity. So this is a bit different compared to things like bubble sort, which have a constant space complexity. When we talk about merge sort, as we have a larger array, we have to store more arrays in our memory, not in our memory. We have to use more space. So that is a trade-off. Now usually we care about time complexity, but if space is a consideration, then absolutely something like merge sort takes up a lot more space compared to bubble sort or any of the other earlier sorts. Okay, so that is big O of merge sort. Next up, we have a whole other fun sorting algorithm. See you then. Welcome back. We're moving on to our next intermediate sorting algorithm, which is called quicksort. So it has a bit of a catchier name. It sounds better than merge sort. Who doesn't want a sort that is called quicksort? have to admit, personally, this is the bane of my existence as far as sorting algorithms. Not because it's bad, it's very useful, as we'll see later on. It's efficient, it works well, it is indeed quick. But for some reason, my brain just does not like the way that quicksort works. Anytime I have to teach these sorting algorithms, I usually, the night before a lecture, will go review, make sure I remember how everything works, I can rewrite the code, and occasionally, I'll have to reference previous code or something. But with quicksort, every single time, I have to double check my work. My brain just rejects storing it. It just won't. It does not like it. So not to poison your opinion of it ahead of time, because I have had many students who really love quicksort. Just for me, the way my brain works, it's just not intuitive. So we're going to spend we're going to pay special attention to trying to understand it and make sure we step through it. Okay, so quicksort, it works on the same assumption that merge sort does. It's one that's going to be easiest to solve through recursion, where we keep basically splitting up the data, the array, until we hit arrays that are 0 or 1 item long, which means that they are individually sorted. We have an array with 1 item, it is sorted. So that's what we take advantage of, but we do something different. We work by selecting a single element, which we're going to call the pivot point. So in any array, you pick any element. It doesn't actually really matter. We'll talk about some of the implications. But let's say we pick the element in the middle. What we're going to do is move all the numbers that are lower than that number to the left of that number, and all the numbers that are greater than that number to the right. Now we're not going to sort them all. We're just going to move them to one side. And then from there, we know that that one number is in the correct spot. That is only that one number. All the other numbers on the right side of things, or the left side, but we don't know the exact position. So then we repeat the process for the left side and for the right side. So if that explanation makes 0 sense, I don't blame you. Let's take a look at a little diagram. So if this is our array, we have 8 elements, 1 to 8 are numbers, and they're in a random order. What we do is we just pick some element, and for this example, we're going to pick the first one, which is 5. And then move all the numbers that are less than 5 to the left of it, and all the numbers that are greater than 5 to the right. So if we count the numbers that are less than 5, we have 1, 2, 3, 4 numbers. So that means that we should have 1, 2, 3, 4 here. We're going to move them all here, and then at this index right here, we'll move 5. And then on the right side, we'll have 7, 6, and 8. We click the next step. That's what we've done. So 5 is in the correct spot. We know that in our sorted array, 5 is going to have index of 4. 0, 1, 2, 3, 4. These aren't sorted, this isn't sorted, but this is sorted right now. So now we recursively repeat the process on the left side and the right side. So on the left side, let's just start again. It doesn't really matter what we pick. It will work no matter what. But let's pick the first item again and put that in the correct spot. So that means it's going to be an index of 0, 1, 2. Because 1 and 2 need to come before it. And that's what we end up with. So now this is in the correct spot. We know in our final array, 3 is going to have index of 2, 5 is going to have index of 4. Then next, we have an element of 2, an array of 2 elements. This is nice and easy. So we pick the first element, which is 1, and we figure out where it needs to go. And that all that we have is one other element, which is greater than it. So the right side now becomes 2, and we can sort that, and it's a single element. So we've now put the end on our left side. And if you kind of look, imagine putting these all on the same line, we end up with a sorted array. At least the left side of the 5. Then we have to get to the right side. So remember, all the way at the beginning, we split right there. We just took care of this. Nope, highlighting the wrong thing. Okay, my computer doesn't want me to highlight that. We took care of the left side here. Now, let's get to the right side. So we pick the pivot point, which is 7 in our example. And we have to figure out, okay, where should 7 go? What's the index? Where it should end up? We move the other elements. So we move 6 to the left of it, 8 to the right of it. And those are both single element arrays now. And actually, if you look at what we have, 1, 2, 3, 4, 5, 6, 7, 8, we have the sorted array. There. I got ahead of my slides. So this shows us how it works roughly. It makes sense, I think, in a nice little diagram, but when we actually start working and trying to write the recursion and visualize it, when we have code, it can be a little bit tricky. Okay, so I have Visual Algo pulled up with Quicksort now. So here's another visualization. We start with this unsorted array, and we pick 11 as our first pivot point. So we want to move all the elements that are less than 11 to the left of it, and all the ones that are greater to the right. So we start and just compare it. Okay, 40 is greater than, greater than, greater than, greater than. Okay, here's a 10. So that's less than. So what we're going to do, this might seem, you might think that we would swap them or something. What we're actually going to do is keep track of how many elements are less than 11. So far it's 1 element. And then we're just going to swap 10 and 40. But we're mentally keeping track of, in our code, not mentally, there's 1 element that is less than 11. Now we keep going. Nope, that's greater than, greater than, greater than. Okay, here's another element, less than 11. So we do the same thing again. Now we know we have a variable, and we say there are 2 things less than 11. So once we hit the end, because there's nothing greater than 11, or nothing less than 11 anymore, now we know, okay, there are 2 things that we added in. There are 2 items that we now need 11 to leapfrog over. And that's what happens. So now 11 is in the correct spot. So does that make sense? We count 1, 2, and then we move to that position. And now everything on the left side is less than 11. Everything on the right side is greater than 11. Now it happens that these 2 values are sorted already, but that's not, our code doesn't know that, it's not guaranteed. Okay, so now our code is going to take the left side and repeat the same thing. So this is showing us 11 is cemented in place. And now it does the same thing with 6 and 10. But this is super short because there's really no values to compare. And so it cements 6, and then it cements 10. But now let's focus on the right side. So next up we have 50, and I'm just going to count how many numbers are greater than 50, or how many numbers are less than 50 as we go through. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. So now we're just going to swap 50 to the end there. Now 50 is in the correct spot, so it should turn orange. Okay? So now we have to sort the left and the right side. There is no right side, so we have to sort this left side. So we pick 27 again. Not again. 27 for the first time. Now we compare it to 43. That's greater than it. Greater, greater, greater. Okay, here's a less than. So we swap, and we keep track of, okay, there's 1 element that was less than. Keep going. Here's another swap. Now we have 2 elements that were less than. Keep going. Now we have 3 elements that are less than. And finally 4 elements. Now where do we put 27? Well, we know that we had 4 numbers less than 27. So we swap it together. Alright. So I'm not going to walk through every other step. I'm just going to fast forward. But you can see 27 is now in correct position. Now we do the left side. Keep going. Now we do the right side. 43 is in the correct spot. 42 in the correct spot. Okay. And we're almost there. There we go. Fully sorted. So it's kind of, this is why, for me personally, maybe that made more sense to you, but trying to write this in code can be very intimidating. And I'm going to give you the pseudocode in the next video, but it's not at all the expectation that you just go and write it. This is a hard one. So the actual is not that long either, but just conceptually it's long. So I'm going to give you the pseudocode. If you want to attempt it, go ahead. But also, don't beat yourself up, please. Welcome back. In this video, we'll write the first part of Quicksort. Just like with merge sort, we implemented the merge helper first. We're going to do the same thing here. You might hear this called partition or pivot. It does the same thing. So we're going to write a function that, given an array, it designates an element as the pivot point, and it should rearrange elements in the array. So this is basically what I already said. Got ahead of myself. And ahead of the slides, surprise, surprise, all values less than the pivot are moved to the left, and all values greater than the pivot are moved to the right. But the order on either side doesn't matter. It just needs to be less than the pivot and greater than the pivot on the right side. But inside the left and right, it doesn't matter what order they're in. So the other really important thing is that this helper should do it in place. So it should not make a new array. And it should return the index of the pivot. So it returns the index. It does everything in place, so don't make a new array to do it. So the first thing to discuss, picking a pivot is actually an important decision. the runtime of quicksort can change depending on where you pick the pivot from. Ideally, it should be chosen so that it's the median value in the data set, if that makes sense. If we could perfectly get it, we would pick the middle value of our sorted data so that the left and right side should be equal. But that's not very easy to do. We don't know what the data itself is and how it's ordered. That's the whole point of trying to order it. So there are other strategies. You pick the first element, or the last one, or the middle, or a random element. For simplicity's sake, in this video, we're just going to always choose the pivot to be the first element. That does actually have some consequences with, as far as big O that we'll talk about later. But we're going to just pick the first element to make it simple. So here's how it could work. If this is our array, and we call our pivot function of that array, it should return an index of 4. So notice it doesn't return the array. But if we look at the array, it's been changed. Any of these configurations are valid. So what it does is it takes the first element and chooses that as a pivot, so 5. And now it needs to rearrange the array so that 5 is in the correct spot, where every number to the left is less than 5. So if we look at all these examples that could be the value of array, it doesn't matter the order. If we have 2, then 1, then 4, then 3, or 1, then 4, then 3, then 2, and so on. As long as we have 1, 2, 3, and 4 on this side. And then on the other side, we have 6, 7, 8 in some order. Now this isn't all the possible options. I just didn't want to go and list every single possible combination out. But it's important to note, it doesn't matter for our code what we actually have on the left side, or excuse me, it matters what we have. It doesn't matter exactly the order that it's in on that side. So these are all acceptable. All that matters is that 5 is in the correct spot. And we return the index, which is 4. 0, 1, 2, 3, 4. So this is basically saying, in the final sorted array, if you kept doing this on the left and the right over and over and over, 5 is in its final position. This is where it's going to be once you sort the data. Okay, so here's the pseudocode. Here's one version of it at least. So write a function, call it pivot or partition, and it accepts 3 arguments: an array, a start index, and an end index. Now we have the start default to 0, and the end default to array length -1. Then we're just going to pick the pivot from the start of the array. Remember, and we could change this to be from the middle or the end or a random place, but for simplicity's sake, we're picking from the very beginning, and then store the current pivot index in a variable. So this is going to keep track of where we're going to swap that pivot to at the very end. So I'm going to walk through on the next, in just a second, on visual algo and show you what I mean. But we're going to loop through the array from the start until the end, and if the pivot is greater than the element that we're looking at, we're going to increment that pivot index variable from up here, and then swap the current element with the element at the pivot index. So it's a nightmare to just read this pseudocode, but it will make sense once I show you an example. And then at the very end, we swap the pivot that we started with the pivot index. And then we return the pivot index. So rather than just talking about text, let's look at it. So at the very beginning, we're going to pick the first element to be our pivot. We start at 28. Then what we do is loop through every other element, and we compare 28 to 41 in this first case. 41 is greater, so we actually don't do anything. And then we get to 4. 28 is greater than 4, so we know that we need to have 4 on the left side of 28. And we're just going to keep a mental note. We're going to have a variable called pivot index, and that's going to keep track of how many things are less than 28, so that we can then swap 28 at the very end to the correct spot. So we move 4 over, and then you have this pivot index that currently is going to be equal to index of 1. So if there was nothing, ignore everything on the other side of the array. If there was nothing else, we know that 28 needs to be in this position at the end, so that 4 can be less than. But if we keep going, 11 is also less than 28. So we're going to swap that with 41. And now increment the pivot index by 1. So now we know, okay, there are 2 things less than 28. Go again. Oops, didn't click it. There we go. 16, that's less. So we swap. And now we know there are 3 things less than. Again, we swap. There are 4 variables. There are 4 pieces of data in this array, 4 elements less than our pivot. Nope. Okay, here's our 5th one. We swap. We go again, and again, and again. And here's our 6th element that is less than 28. So we swap. Now we've hit the end, and we have this pivot index variable, this mental note I mentioned. and is now equal to 6, because every time we found an element less than 28, we added 1 to it. So we have 1, 2, 3, 4, 5, 6. This tells us we need to swap the element at index of 6 with our pivot, which is at the beginning. And if we do that, there we go. Now we're done. All we have to do is return this index. So everything on the left is less than, everything on the right is greater than. The pseudocode on its own isn't all that helpful, but if you look at this side by side with something like this, where you step through it, I think it can help. So go ahead and implement this if you'd like to. Again, it's not all that easy, but give it a shot. If you want to stick around, I'll do one more example walkthrough, but I know that it can get boring if you understand it all and you're ready to go, or you're just bored, go ahead and skip this. But I'll put it here for extra practice. New data. At the very beginning, we pick our pivot point, just the first thing, 26. Now we compare it to every other element. Now 23 is less than 26, so we're going to keep track of that. We have that counter pivot index, and we know at the very end, at least, we're going to have to swap 26 to index of 1. We get to 27, that's greater than, so we don't do anything. That's greater than again. Now we get to 17, which is less than. So what we do is we swap with 27 in this case, and then we're going to increment our pivot index by 1. So now we know there are two things less than 26, so we need to swap at the end, so 26 is here, where 17 currently is. We go through again, that's greater than, greater than, greater than, greater than. Finally we get to 1, which is less than, and we swap with 44. And now we increment pivot index by 1 again, so now it's at 3. So at the end of our code, we're going to swap the pivot at index of 0 with the pivot index, which is 3. 0, 1, 2, 3. So we swap these two things, and voila, now we have the left side correctly partitioned and the right side. So 26 is at the correct spot. And our code should return index of 3, which is saying that the correct spot for 26 in this array is index of 3. Alright, welcome back. So let's start by defining our, not in caps, our function called pivot, and it accepts an array. We have a start. You can go back and look at the pseudocode, which should default to 0, and an end defaults to array.length plus 1. And then here's my sample call. So pivot of this. Take a moment and figure out what you think this should return. Pause it if you'd like. What it should return is the index 3, because it's going to take this first item, which is 4, as our pivot, and figure out the correct index that it should be in. So if we look at the sorted array, like this is the final array of these numbers. This will not be returned from this, but from our eventual quicksort it will be. If you look at where 4 is, that's the index of 0, 1, 2, 3. So our code should return the index of 3. Now the array, it could look like this at the end, but more than likely it will look like this possibly, and then on this side we might have 8, 6, 7, 5. All that matters is that 4 is in the correct spot. So anything on the left just needs to be lower, anything on the right is greater, but the order doesn't matter. So the first thing we'll do is define a variable called pivot. And remember that our example, we're starting with the pivot always as the first element. So if start defaults to 0, we'll set this to be array of start. So we start with 4, for example, as our pivot. Or if our array looks like this, it would be 10. We start with that, and then we're going to make a variable called swap index. Now swap index is going to keep track of where we're going to swap this 4 to at the very end. And also it's what we're going to return. This is going to be the index. In our case, it should be 3, hopefully, at the very end that we return. So I'm going to start it at the beginning, index of 0. So it starts at 0. Now, we need to loop over every item in this array, but there's no reason to loop over this first one and compare it to itself. So let's loop over everything after start. So that means 4 var I equals, instead of 0, to start plus 1. While I is less than array.length, I plus plus. So rather than doing 4 and comparing it to 4 and then 8, just do 4 and start off our loop right here. Now all we want to do is compare our pivot, so that's going to be 4, so if pivot is greater than, we want to compare it to array I, the next element that we're looking at. So our first time through, is 4 greater than 8? No. So we're actually not going to do anything. Next time through though, we're comparing 4, and now I has gone up to the index of 2. So So we compare 4 and the value of 2. 4 is greater than 2. So what we'll do is increment swap index by 1. So this tells us, okay, there's one thing at least so far that is less than our pivot. But then we're also going to swap 2 with 8. Because our swap index is 1, all we have to do is swap array I with array of swap index. Does that make sense? The swap index was 0. Now we found the first item that is less than 4. So we increment the counter, just keeping track of how many things are less than 4. Where are we moving 4 to at the very end? So now it's equal to 1. Anyway, now we need to swap. So now what I'm going to do is just copy in any swap function. This is our basic one. It just takes an array and then 2 indices and it swaps the values in that array. And I'm going to put it in a function because we're going to actually use it more than once in our code. So we're actually almost there. What we're going to do now is swap the array inside of it, the swap index, followed by I. So our first time through, the first swap we make is 2, which is I of 2, actually, the same number. And then we're going to swap it with swap index, which is 1. Okay, so then we repeat the code. Next time through, we compare 4 and 1. Well, 1 is still less than 4. So this time, we increment swap index again. So swap index is now 2. And then we're going to swap the item at index of 2 with the item at index of I, which means we're going to swap 1 with the item that's here, which is actually 8. So if we were to visualize this whole thing, we start off like this. And the next time through, we don't do anything with 4 and 8, but then we do swap 2 and 8, like that. And then the next time through, we're comparing 4 and 1. Well, 1 is less than 4. So we swap 1 and 8, like this. Now our swap index is right here. So at the end of the code, if there was nothing less than 4, which there actually is, but if there wasn't, at the very end, we're going to swap 4 and 1. And if we did that, we end up with all the numbers less than 4 on this side, ignoring the fact that we still have to account for 3. So we keep going. Next we compare 4 and 5, nothing happens. And we compare 4 and 7, nothing happens. 4 and 6, nothing happens. 4 and 3. This time, 3 is less than 4. So what do? We take 3 and we swap it with our swap index, which was right here. So now we swap 8 and 3. So we added 1 to our swap index, which now makes it index of 3. Which we guessed also is the value of 3. That's confusing, but this is our swap index. So the very last thing we have to do after our loop is take that last swap index and swap it with the start, like this. And now 4 is at the correct position. So basically all that we've been doing, we keep going through here, we move things over to the left, we swap them anytime it's less than 4. But we've left 4 at the first position, so at the very end, we can just swap 4 to the correct spot. What do we need to do now? Well, if we actually just printed out array, I think this would make it clear for us. You can see here, start off, I'm only printing it out when we do the swaps, but you can see the final state is this. And then we need to do our final swap, move 4 and 3, swap them, and then we need to return that index, or swap index. So let's come down here after the loop and add in our final swap, which is in the start of the pseudocode. Swap the starting element with the pivot index. So we just do swap, which again is coming from here. And what are we going to swap? We're going to swap the array, the start, and then swap index. So we're not swapping the pivot because pivot is the value. The start is the index of that pivot. So this is kind of a headache. So let's try and walk through. Totally recognize that. Let's just make sure it works first. We need to return at the very end swap index. Remember, that's the whole point. It needs to return the swap index. We run it. It returns 3. And if we start off with a different number like 9 here, it returns 8 because 9, the correct location is at the very end of the array, index of 8. We'll go back to 4. So we get 3. If we constant log the array at the very end, we should see 4 is in the correct spot. All the lower numbers are before it, all the greater numbers are after it. So that's our pivot helper. So kind of a lot of work. So now that we have that done, we need to move on to the actual sorting part. We're doing this one time. We need to repeat this on the left side, and then on the right side, and then repeat that, and repeat that until we hit the one item arrays. So we'll get there. Oh, and before I forget, here is the ES 2015 version where we just use our fancier version of swap, and I use let instead of var, and that's pretty much it. The same exact logic. It still works. We still get 3. So I'll leave them both in there. You can use the one you prefer. All right, next, quicksort. All right, welcome back. So in this video, I'm going to quickly run through the pseudocode for quicksort, but it's pretty short, so I'm actually going to just implement it too, rather than doing a separate video to show the pseudocode and then implement it, just to keep things a little briefer. So we have our pivot helper finished. You pass in a full array, or any array, and it's going to take the first item and figure out where it should go, and then put all the smaller items to the left, all the bigger items to the right, and then return the index. So that's important that it returns the index, because what we're going to do in our quicksort function is that it's going to call that pivot helper at the beginning of the full array, and we'll find out, index of 4, for example, is the first pivot point. And then what we're going to do is recursively call the same thing, call quicksort again on the left side and on the right side of that pivot point. So imagine we call quicksort with this array. Well, the very first thing that happens is that we find the pivot, which is 4, and that is moved to this index right here. And then what we're going to do, there we go, is we're going to then call quicksort on this side from 3, the beginning, up until, but not including the pivot, because we already figured out this is in place. We don't want to move this. So we're going to sort the array here and here with quicksort. So the rough logic, when the helper returns the updated pivot index, we recursively call the pivot helper on the left side and then on the right side as well. Now it's important to notice, or to point out, we're not making new arrays. This is all happening in place. We're not making new arrays. It's happening in the same array. So our base case, it's not quite just to check if the array is item of length, or if the array has one item in it. It's to check if the sub-array has one item in it. And what that means is we're always going to be working with this array, for example, but we're only going to be looking at this portion, or this portion, or eventually this portion. And so what we're going to check is not to see if the length of the array is 0, or is 1, because this length will always be the same. We're not adding or removing elements. We're going to check if the start point that we're looking at, and let's call it left and right. If the left and the right are equal to one another, or if the right is less than the left. So that happens when a subarray has less than 2 elements. So I'm just going to implement it. This is a tough one, honestly, to just take that pseudocode and try and write it yourself. I applaud anybody who wants to do it and who tries it out. But again, no expectation on my part that when I teach this in person, it's very rare that anybody can implement it right away. And even once I show the code, it can be hard to come up with it again. And I've already mentioned my struggles with it and how it's just unintuitive for me. So I'm going to define my function quicksort. I've already done that actually. And it's going to take an array. And the first thing that we'll do is call, so let's make a variable called pivot index. And it's just going to be equal to calling pivot with that array. The thing is, our pivot, first of all, we go back, it accepts an array, a start, and an end. And this is important because the very first time through, yeah, we want to call it on the whole array. Then this recursive function eventually is going to call again on this subarray, or this one, where we have a different start and end point. It's not just the default 0 up until the end of the array. So what I'm going to do is in here, I'm going to make an argument called left instead of equal to 0, and another one called right, which is array.length minus 1. And then we're going to pass in left and right when we call pivot. So the first time we call this right here, the default value for left is 0, and for right is going to be 0, 1, 2, 3, 4, 5, 6. So we're calling pivot on this array with 0, 6, right? So then that goes with the bracket, takes the first item inside of that pivot function, and it figures out that this needs to actually be an index 3. So it changes the array to look like this, and it returns the index of 3 to us. So pivot index is equal to 3 at this point. Then we want to repeat the same thing, but we want to do it on the left side, which basically means from the left, the start point, which right now is 0. So from the left up until the pivot index -1. So we already have this cemented in place. We want to now sort from here to here. And then the same thing on the right side. But we want to go from pivot index +1 up until the end, the right. So let's do the left first. The left side is just quick sort of the array. This time we're going to pass in a left and a right. Unlike down here when we called it the first time, they defaulted to 0 and then array.length -1. This time the left that we're looking at is still going to be the same left that we looked at before, the 0. But next, the right, where we're going to stop, is going to be what we've already discussed, the pivot index -1. So that way we don't include that pivot index in there. So this is cemented. We just want to look at that. And the same thing on the right side. Well, not quite exactly the same. Same idea. There's going to be quick sort of the array, but we're going to start at pivot index +1. So that means this is our index. We want to go from here until the end. So pivot index +1 until right. So those are the recursive calls. However, if I just run this as it is right now, there's a big problem. It's going to run forever. So actually, if I do this, we get our Stack Overflow maximum call stack size exceeded, because there was never a base case. Nothing was ever returned. Nothing ever stopped this recursive call. It just keeps going and going and going and going and going. So where do we want to stop? We want to stop in this situation, where we've hit a subarray that is one element long. And how do we know that? Remember that at any point, if we look at that array, it's always the entire array. We're sorting it in place. So even at this step right here, for example, array is still the entire array. What has changed are the left and right, because left and right are constantly changing as we're calling quick sort recursively, because left and right are based off of the pivot index. We're getting a new pivot index each time, left and right are changing. And so as these subarrays become smaller, left and right get closer together. So for example, here, left was 0 and right was 6. Then here, for example, left was 0 and right was 2. Here, left is 0, right is 1. Now here, left and right are the same. So our conditional, we want to keep doing this code, keep running if left is less than right. And so as soon as they are equal, as soon as left is now equal to right, that means that we're looking at one element. Does that make sense? Remember that left and right are just pointers inside of this full array. So it started like this, and then on one of them, the recursive call moved to this, and then to this, and then it became the same thing, and that's when we stop. So that means that we've hit the end, at least of one of the branches. So I need my bracket there. There we go. Okay, so we're still not quite done. We have one missing piece, which is really important. We're not returning anything. We need to return array at the very end. Just remember how these recursive calls work. This quick sort here is waiting on the results of quick sorting this, quick sorting that. And then those in turn are waiting on the result of quick sorting this and that. We have to return the array here so that we can get it back here, keep going up, and then the same thing on the right side. So let's save, and I'm going to put in also, let's see if it works. Oops, not clear 0. There we go. Let's see if it works now. And it looks good. We're getting 1, 2, 3, 4, 5, 6, 9. Not sure why it shows that. And let's just verify. Let's start to head up a little bit, but negative number in here. Alright, and it looks like it's working. Alright, so lastly, let's just step through all that, visualizing what actually happens with the Chrome debugger. So I have a simple array with 6 elements in it, and all that we're going to do is execute it. So from a breakpoint, command enter, and I'm going to step through it. So first up, at the beginning, is our array. Left is 0, 5, the right is 5. It's the last index. That makes sense. Now, we're going to, because left is less than right, we're going to call pivot. We'll put 5 on that array. So we're going to pivot. And at the end, so we fast forward, we get to swap index is 2, which is returned. And the array now looks like this. 4 is at index of 2, and 2 and 1 are to the left, and 6 and 5 are to the right. So we return that. Then we get to this line. We have pivot index now 2, we just calculate that. And the array looks like, now we're going to do a sort of this array. But from the left means I'll pivot index minus 1. So if you watch the call stack, there's a new call of quicksort on top of it. The left is 0 and right is 1. So now we're looking at these and so we do the same thing on the pivot. The pivot index is 1, so we return 1. And then move on. And there's a new quicksort that's been added. This time we're going from 0 to 0 of this array, which now left is not less than right. So what does that mean? It means that we return the array. So now this is the array that gets returned back to the previous quicksort, which was waiting for this side, the right side. So now the array looks like this, 1, 2, and 4. The left side is sorted. So this quicksort is now waiting to do the right side. So pivot index is 1. So this quicksort is the second part, is the right side. So when we did these two elements, we did the left, and now we do the right. The thing is that there is no right, because right is less than left. So all that is returned is the array again. As you'll see, it's unchanged. 1, 2, 4, 6, 9, 5. We go back to an earlier quicksort that was waiting. And this time, there we go. And now we're sorting the right half. So pivot index is 2, which is right here. And we're going to call sort the array from pivot index plus 1, meaning index of 3, up until this, the end. So here we go, we call it. And you can see that now, this time around, left is 3 and right is 5. Now we find the new pivot. Find that the pivot index is 4. This is what the array looks like now. So we found that 6 is our pivot. We put 5 to the left, 9 is on the right. We return the value of 4. So back here, we now have a new pivot index of 4. We're going to take that index, and now we're going to sort on the left side, which is really, if you look, it's from 3, which is the left, until our index was 1 minus 1, so 3 to 3, as you can see here. And what does that mean? Well, left is less than right. We do a quick stack on the stack, quick sort on the stack. Left is less than right, so we're going to return that array as it is. And then we get to our next one, quick sort on the right side, which also is going to be sorted, because you'll see that left is 5, right is 5. That means that we need to just return the array, which is what we do. And then we expect the next quicksort, which is waiting to return an array, which now has been updated to return the array. And we're on our final, this is the original call. And now we have both sides finished, left and right, and we're finally going to return the array. And here's the return value. And there we go. 1, 2, 4, 5, 6, 9. Congratulations on not quitting this video early if you made it. It's a lot. That's the basics of quicksort. Welcome back. Our last video on quicksort. If you have minutes, if you ask me, we're going to talk about the time complexity and space complexity of quicksort. So first off, notice that best and average are both O and log n, which is the same as merge. And if we look at log, let's look at best case, for example. So here's our array, and we have to make a decomposition, and then another decomposition, another one, just like the merge sort, where the pattern here, as n grows, we have to make log n, log base 2n decompositions. So as we have more elements, for example, 32 elements, we have to make 5 decompositions, slice it down 5 times. If we are, and this is the best case, remember, we're going to see the worst case in just a moment. If we have, I don't know, let's say 64, we would have to make 6 decompositions. So that goes at the rate of the rate of log n. The blend, each level, each decomposition we make, both n comparisons per decomposition. So that's happening when we're pivoting, we're finding that we're comparing every other element one time. So that is how we get n log n. Very similar, it's the same reason really why we got n log n with merge sort. Now let's talk about worst case. So our algorithm, our pivot function, already sorted. So here's the worst case for our current
vaccine.
If we have this array, we're trying to sort it. And of course, our code doesn't know that it's sorted. So we take this in, and the very first thing we do is find the first item and use that as the pivot. Well, we compare it to every item in that array, but nothing is less than it. So the next array, that decomposition really only gave us a single item. We have this entire subarray left. So every time we go through, each decomposition is only one item that we're pivoting on. And so everything moves to the right side with our current algorithm. We have to keep going and going and going over and over and over because we're only taking the first item and it's already sorted. And then for each one of those, so that is n decompositions. The worst case with our current setup is O of n decompositions, and on each level, each decomposition, we have to make O of n comparisons, which results in O of n squared, quadratic time, for the worst case. So basically the problem arises when the pivot is chosen, when the pivot that is chosen is the minimum element every single time, or the pivot is always the maximum element. So to fix that, in this example at least, if we're dealing with a sorted array, we can get around it by, instead of pivoting around the first item no matter what, pivot around a random item. Just pick anything in here, it doesn't matter. Just pick a random item. Or try and pick the middle element every time. And that way, even if we have a sorted array, we can avoid the problem. But of course, there's still a chance that if you pick the middle element every time, it's possible that the array is unsorted, and it's supposed to be in random order, or we think it is, but somehow we're always picking the minimum every time. We can never avoid that worst case entirely, because the way the algorithm works, if you're pivoting around the minimum or the maximum repeatedly, that's going to be quadratic time. But we can just do our best to avoid chances of constantly picking the minimum or the maximum, which is why you do a random number or the median instead of the first element every single time. But by doing that, what we did, picking the first element every time, it allowed me to illustrate this problem, the worst case scenario. So take a deep breath. That was quick sort. That's a lot, I know. Again, do not feel any pressure to be able to write that on your own. It's really more about understanding how it works. Being able to walk through. If you had a whiteboard, could you write down the values of the array each time through? Could you diagram out the recursion? That's the sort of thing that I hope you took away from this. Okay, moving on. All of the sorts that we've seen so far are grouped together in a group comparison sorting algorithm. All that means is that when we're talking about bubble sort or something more advanced like quick sort, at the end of the day, beneath the surface, the base comparison that we're doing is between two items at any given point. So we have one item on the left, let's say, and another on the right, and we're deciding which one comes first or which one comes second, depending on how we're sorted. So a comparison sort just means we're comparing two things. That's the most we ever compare at a given time. We're doing less than versus greater than. And then we're deciding where that one item goes. So when we talk about average time complexity for something like bubble sort, it's O of n squared, same for insertion and selection sort. Then we saw a slight improvement, well, more than a slight improvement. We saw a pretty big improvement with quick sort and merge sort, which had average time complexity of O of n log n. So the question is, are there faster sorting algorithms? Can we improve upon O of n log n? Can we do better? And the answer is sort of. The answer is yes, we can, but not by making comparisons. So mathematically, there is a lower bound, an asymptote, for our average time complexity in a comparison sort. So no matter what the actual comparison algorithm is, sorting algorithm is, quick sort, heap sort, shell sort, any of the ones we've seen, cocktail shaker sort, haven't heard that one. All of these, well, not all of them, some of them are slower, like we saw with bubble sort, but the best average case time complexity that we can ever hope for in any comparison sort is n log n. If you want to learn more about the reason for it, you can read this Wikipedia article. It goes into a little bit of a proof down here that explains how we arrived there. It all has to do with the limited information that we can gain from a single comparison. There is a mathematical bound to that. Anyway, that's not really the focus here, because we have a solution. We have a way around this, but only in certain cases. So there are other types of sorting algorithms that are not comparison algorithms. And these algorithms take advantage of special properties of the data. For example, there's a group of sorts called integer sorting algorithms, and they only work with integers, with numbers. And we don't actually make direct comparisons. So one of those is radix sort. So when I say that we don't make direct comparisons, I mean we're never actually comparing, is this number less than this number? Is this number greater than this number? So we end up sorting the data in a different way. So radix sort is kind of fun, and it's very different than anything we've done so far, because we're not making comparisons. So let's talk about how it works. So I mentioned it's a special sorting algorithm that doesn't make comparisons, and it works on numbers. So usually when this is actually used, it's used with binary numbers. Any number can be expressed in binary. Also, you can take any strings or images if you wanted to and convert them to binary. So it's possible to sort other data, but the actual data we work with at the time that we're sorting it needs to be numbers. And we're going to work with base 10 numbers like 950 or 17. So it never makes comparisons between two elements. It never asks what's smaller, what's larger. Instead, it exploits the fact that information about the size of a number is encoded in a number of digits. What I mean by that is that if a number has more digits, let's say a 4-digit number, it's larger than any 2-digit number. It doesn't matter what the two numbers are. We're not comparing the two numbers, but we know that something with more digits is larger than something with fewer digits. So here's actually how it works. We actually take a list of numbers. Let's say this is what we're trying to sort. We have some numbers that are 1 digit. These are all base 10, 2 digits, 3 digits, 4 digits. And we create 10 different buckets. And these buckets represent all of the possible numbers, the 1-digit numbers in base 10. So 0 through 9. So for every spot in a number, it could be 0, a 1, a 2, all the way up to a 9. And what we do is we go through the entire list of our numbers, and we start by looking at this digit. So the first digit in the number from the right side. So 6, 4, 6, 3, 8. Okay? And we group them into buckets based off of that number. So you'll see all numbers that have a 2 in the rightmost position go in the 2 bucket. All numbers with a 6 in the rightmost position, whether they're 2 digits, 100 digits, it's just that we're looking at the rightmost digit. We group them together here. So we're not sorting them within this bucket. You can see that these are not in order. We take all 7s, all 8s, all 9s. And then we form them back into a list, keeping the order that they're in right here. So this will be at the beginning, and then this number, and then this number. you can see here. So the numbers that had 2 as their last digit come before the numbers that had 3 as their last digit. And then at the end, we have numbers with 9 as their last digit. Now we repeat the process, except we look at the next digit to the left. So we're going to look at this digit, and this one, and this one. Okay? So now we group them based off of that second digit from the right. So if we look at this column, this bucket, we're talking about 0, which this has a 0, 408 has a 0 in that position, 902 does. Then these numbers, which are one-digit numbers, don't have any digit in that position, so we just put them in the 0 bucket. There's a 0 there, right? We could write any number as 07 is the same as 7. 04 is just the same as 4. So then we end up with, if we go over here, we've got all the numbers that have 5 in that position, all the numbers that have 8 in that position, and we're getting closer each pass through here. We're never comparing the numbers to one another. And now we reform them into this list. You can see it's getting closer to being sorted, but we're still not there. So we repeat it again, where we're talking about the third digit. So the first, the second, the third digit. Do it again. Okay? So you can see the smaller numbers are already grouping up here. Then we have, for example, here, 5. This number has 5 in its third spot, and so on. And then we reform it into a list again, and then we have to go one more time. So the number of times you have to actually do this process depends on the largest number, how many digits it has. So we have a couple of 4-digit numbers, so we have to split them up 4 times. If we had a 10-digit number in here, we'd have to do it 10 times. Okay? So here's our last time. So now they've been split up, we're talking about the 4th digit. None of these have a 4th digit. This one does, and so on. And then we form them into our list, and we're done. So when I say we form them into the list, I mean we just take the order that's already in these buckets. So we start here, then here, all the way up to 902, and then we take this bucket. This one is empty, so this one, we keep going, and now the numbers are sorted. So we never made any comparisons between the numbers in our list. Instead, we took advantage of the special property of numbers. So lastly, here's a nice animation of radix sort. I'll hit play. What we do is we take a look at that rightmost digit and we group them in those 10 buckets. So if we're talking about base 7 numbers instead, we would have 7 buckets. We're talking about base 10, so we have 10 buckets. Okay? And now we reform them. You can see the order we're talking about. We just pull them out of the buckets in the same order that they're sorted. And now we take a look at the second digit from the right, and we form them into buckets. Okay? And again, in this case, our largest number is a 4-digit number, so we're going to have to do this process 4 times. So that was 2 times down. Now we have 2 more. So now we take a look at the third number from the right. And numbers that don't have a number in that position, we put them in the 0 bucket. And we're almost there. We just have to take a look at the 4th digit from the right and group things into the correct bucket based off of that digit. So we're almost there. So a couple things to keep in mind. In order to make this work, you have to be able to figure out a digit in a number at a given position. So in the next video, I'm going to talk about some helper functions we need to write. For example, I need to be able to ask, hey, what is the second digit of this number? What's the 4th digit or the 1st digit? And most languages don't give you an easy way of doing that. We have to write our own method to do it. So that's what we're going to start with before we get to the buckets. Anyway, that's radix sort. It is a special case of a sorting algorithm that is not a comparison sort. It's an integer sort that works because of a special, I won't say loophole, but a special property. And it allows us to sort numbers very fast compared to having to do comparisons. Anyway, we'll implement it in the next couple of videos. Alright, now that we have a basic understanding of radix sort conceptually, we need to implement a couple of helper methods so that we can actually write the main algorithm. And the first one that we have to do is called getDigit, or something like this, that takes a number and a position and returns the digit at that position. So we might have 1, 2, 3, 4, 5. If we called getDigit 1, 2, 3, 4, 5 with 1 as the position, that should give us this number. So this is the 0 position, the 1, the 2, 3, the 4. So it's not a string or an array. We start 0 over here, and we move to the right, this is going the other direction. And get digit is really important for sorting things into these buckets, right? If we have, starting the very first pass on this list, we need to take a look at this digit, the 0th digit in our example, and put things in the correct spot. And the next time through, we need to look at this digit. So we need a method that will give us that digit. And unfortunately, there's no easy way of doing that out of the box. We need to write a method. So if you want to do this on your own, rather than breaking this up into 3 different videos for the 3 methods I'm going to show, I think I'm just going to combine them into one. I know that I'm going to combine them into one. I'm already recording it. The focus is not about this logic. The focus is on the sorting logic of radix sort. But anyway, if you do want to try these, pause the video and do it now. 2 strategies. You can do, you can convert to a string, and then use the correct index to access the number you want, and then convert it back to a number. The only problem is that, as I already mentioned, the strings are indexed from the left side, so if somebody asks for position 0 of this, if you convert to a string and you get 0, well, that's going to be the complete wrong side. So you can do some math so that you can convert working backwards using negative indices or something like that, then come back to a string. Or you can do some math. So this should only work with base 10 numbers, by the way. You don't have to make it work for binary. We don't need a user, if we were doing other bases, a user could pass in what base, but assume base 10 numbers. So there's some math you can do. Each one of these positions represents a power of 10. This is the 10 to the 0th position, 10 to the first, 10 to the second, which the way I learned it in school was not 10 to the second, 10 to the third. It was the ones place, the tens place, the hundreds place. So what you can do is divide by that power of 10, and then do some other math, which I'll show you in just a second to get the answer. Okay, so if you want to implement it on your own, pause it. Otherwise, here's a spoiler. Here's a solution. I just took this from Stack Overflow, and it's called get digit. It satisfies our requirements. Let me show you how it works. Let's say we're taking a look at a number like 73, sure, that number. And if we pass in, so if we did get digit of that, and I'm looking for whatever number is at this position, 0, 1, 2, we'll pass in 2. The math is that this number here is 300, right? It's a 3, but in the context of this, it's a 300. So we're going to divide by 100. As you can see here, math.power 10 to the I. So 10 to the second, which is I, gives us 100. So we're going to divide this whole number by 100. So I'll write this out here. We can ignore the math.absolute value just for a second. That's just so that this works with negative numbers. If I passed in a negative number, this should still be 3. We don't want to get negative 3. This is just 3 is the digit we want. So that's what the math.absolute value is. So we'll ignore that. If we take this number and we divide by 100, which is what this is right here, and then we floor it down here, so we get 73.23. If we do a floor, we just get 73. Okay, so then we have 73 mod 10. So we divide 10 into there. How many times does it go in? Doesn't really matter, but it goes in 7 times. So we get 70. What's the remainder? Well, the remainder is 3. So if we do mod 10, we get 3, and that's what we're looking for. So we divide by the place, the hundreds place, then we floor to get rid of the decimal, then we mod 10. That's the math. So just to prove that it works, on the code, and let's pass it 0, we get the correct digit, also a 3, 1, we get the 2, 3, we get the 7, and if we pass in something that's not in there, we get 0. Perfect. So this works, we're all good. The next helper we need has to do with figuring out how many digits are in a number. And the reason we need that, to go back here, is in this example, we need to know how many times we need to sort things into buckets. How many times do we have to reorder everything? And the answer is 4, because the largest number we have has 4 digits. So that's our bound. If we have one 10-digit number here, then we need to do it 10 times. So we need to write code to figure out how many times we need to run it for a given list of numbers. And all that we need to do is figure out which number has the largest or has the most number of digits. So there's 2 methods we'll write. The first one will give us digit count for a single number, and then the second one will use digit count to figure out the largest number of digits for the entire list. So we'll have max digits, which calls digit count. So digit count, just you pass it a base 10 number, and it should return to you how many digits are in there. So this would give us 3 digits. This is a 2-digit number. This is a 1-digit number. You could do this as a string, convert it to string, find the length, or you could do some math, which is what I'm going to do. So pause it if you want to try and implement this on your own. Very loud motorcycle outside. Otherwise, here's the solution. All right, I copied this solution over. It's called digit count, and there's a couple things we'll talk about here. So first thing first, log 10. This is a log base 10, which what that does, if you didn't watch the log video early on in the course, it's basically asking 10 to what power gives us this number. So if I called digit count on, I don't know, let's do 423. 10 to what power gives us 423? Well, it's not going to be a nice clean number. So that's why we do the floor. But let's do math.log 10 of 423 gives us this. And when we floor that, we get 2, because we're just getting rid of that. So our answer here was 2, and we're close, except that we need to count the number of digits, which we need to add 1 in, so we get 3. So just one more example. We have a large number like this. Okay? We're doing math.absolute value again because we want it to work with negative numbers. If somebody passes in negative, this number still has the same number of digits. We're not going to worry about negative numbers for our sort, but these are from Stack Overflow, and it's always good to be conscientious of that. So if we take this number and we do math.log 10 of that, and then we floor that, we get 4, and we add 1, which is 5, that's how many digits are here. 1, 2, 3, 4, 5. Okay, so if the math is crazy to you, don't worry, it works, and this is something I feel like it's totally normal to just take this from Stack Overflow and add this to your code if you really need it. So digit count, the only special case is if the number is 0. So if somebody passes in, well, not that, but if we did this, this is a 1-digit number. But the problem is that if you try and do math.log 10 of 0, you get negative infinity. That's not what we want. So we have to add this special case in. Okay, that's digit count. And then our last method we need is called most digits. And this will take a list of numbers and just tell us which number has the most digits in it using digit count. I mean, it should use digit count because we just wrote it. I guess it could just do it again. So what I would do is take digit count and run it on each number in this list, and then keep a running tally of what the maximum is, and just return that number. So you don't even have to return which number itself had the most digits, just the count. So for example, in this list, it would return 5, because this is the largest number, it has 5 digits. In this list, it returns 2. All the numbers have 2 digits. So this one's the easiest, I think, because we already have this code, if you just want to copy it. The focus, again, is not on actually writing these yourself, but I just want to walk through them. So most digits, here's my solution. It looks like this. I'll copy it over. And it just takes a list of numbers. And we start with a max variable, max digits. It starts at 0. And then I loop through nums. And I'm using math.max, which if you're not familiar with, you just pass in 2 numbers. If I do 0 and 12, it's always going to give me the larger number. And so this allows me to, instead of doing like an if statement, if x is larger than a current max, then reassign the current max, I'm just setting max digits to equal the maximum between the current value of max digits and digit count of nums I. So for each number. So if I do most digits of, let's see, 23, okay, of this, at the beginning, max digits will be 0, and then it loops through, and it becomes 2, because the largest number we've seen so far has 2 digits. But then next time through, it's 3. Next time through, it's still 3. Then it's whatever this is, and it stays at that. So let's run this. and I get 8, because this number presumably has 8 digits. It does. Just kind of. Yep, 8 digits. Okay, so these are the helpers we need, and now we can actually implement, in the next video, we can implement our radix sort using these. And the logic isn't that bad once we have these done. You don't have to worry about recursion or any sort of crazy logic. You basically just loop over and split things into buckets and then join them together and do that X number of times, where X is the number with the most digits. Okay, see you then. Hey, welcome back. Time to actually write radix sort. So if you watch the video on the helper methods, that's actually the harder stuff. Now we just call those helper methods a couple times in a loop and make the buckets, and that's kind of it. So here's the pseudocode if you want to add this yourself. Define a function that accepts a list of numbers, just call it radix sort, something like that. And then the first thing we have to do is figure out how many digits the largest number has. Well, we just wrote that method, most digits. If we go back here, we need to figure out, all right, which number has the largest number of digits, or what is the largest number of digits in any of these numbers. And in this case, it's 4. There's a couple of 4-digit numbers, or there's more than a couple. So we're going to need to loop 4 times, because we're going to need to sort them into buckets for this digit, oops, this digit, this one, and this one. So 4 different times. If we had a 6-digit number, we need to do it 6 times. So once you figure that out, using the method, which is back here, then you need to start a loop from 0 up until that largest number of digits. So if we're doing this 4 times, you need to go from 0 to 1 to 2 to 3. And each time through, we're going to create buckets for each digit. Now, a bucket is just an empty array. So we'll have an array that has 10 subarrays. That's how I would do it. And they all start empty. So index 0 of this array starts as an empty array. Index 1 is an empty array. And then each time through this loop, we're going to take each number, put it in the correct bucket based off of its kth, that's a really difficult thing to say, its kth digit, meaning that whatever this loop k is, we start at 0, we're going to put it in each number in the correct spot, correct bucket slot, using the 0th digit, and then the first digit, the second digit. So if we go here, right, if we run sort, go, first thing we do, we make these buckets. Here's our 10 buckets. Each one of these is an array inside of one larger array with 10 slots. And this is index 0, this is index 1, index 2. So all that we do for any number, which one's next, all right? So 10, we take the 0th number, which also happens to be a 0. So we take this number and put it in the slot 0, index 0. And we keep going. So here we go, we take the 0th number of this. We already wrote a helper method to do that. We called it, what did we call it? Digit, get digit, something like that. So get digit, index 0 is going to give us 7. So we put the whole number in slot 7. So we keep going with that. And then the next time through our loop, we're going to look at index of 1, and then index of 2, index of 3. And then the other thing we have to do is replace our existing array with the values in the buckets. So this is where we reorder them a bit. So in this example, we put them all in the correct buckets. Let's speed this up a little bit. And then at this point, we reform them into a list using the order that they're currently in. And there's a couple of easy ways of doing that. You don't have to loop through manually and do this. I would just concatenate into a new array. So we just keep that order, and then we start the process over. So there's going to be 2 loops. There's the outer loop, which happens 4 times. So we're looking at digit 1, or 0 in all the numbers, digit 1 in all the numbers, 2, 3 in all the numbers. And then we need an inner loop to actually do something to each number in the list. Okay? And then at the very end, return that list. So I'm going to implement this in the next video. Totally fine if this one is a little challenging. It's always fine. It's not my place to say that. But this is one that I think, if you look at the code itself, the solution, ignoring the actual math from the last video about finding the digits and log 10 and dealing with modulo and all that stuff, the logic in the sorting function itself is relatively straightforward. So we'll do that in the next video. All right. So we have this through code laid out, we have our helper methods written, let's write the logic. So the first thing I'll do, I need my helper methods, I'm going to keep those, and I'm going to define a function called radix sort. And it takes a list of numbers. The very first thing after that, we need to figure out how many digits the largest number has. So we have this method, most digits. So let's make a variable called most digits, or something like that. Max digit, let's do that. Max digit count equals most digits of nums. And then let's just print that out so we can see that it works. Okay, and then let's call radix sort down here and pass in a list of numbers, a couple of small ones, some larger ones. Okay, so what is the max digit count of this? Well, it looks like it should be 4. The largest number we have is a 4-digit number. If you run the code, we get 4. Alright, so now we know we need to loop 4 times. So we can start with that. Loop from k, it doesn't have to be k, but k equals 0 up to that largest number of digits. So let's write a for loop. For let k equals 0, k is less than max digit count, k plus plus. So this gives us an index k going from 0 to 1 to 2 to 3. So we can use that and pass it into this method getDigit. So we can ask for the 0 digit or the third digit. Okay, now that we have that written, we need to make our buckets. So I'm going to make a list. I'm just going to call it digit buckets with 1b. And we could manually construct this, make an array, and then push in 10 empty arrays. But there's also an easy way, relatively easy. We do array.from, and then in here, right here, if we pass in a length, set it to be 10, and then we tell each one to be an empty subarray. So if I just copy this over here and paste it in, if we look at what digit buckets is, it's an array of 10 empty arrays. So if I change it slightly to be an array containing the string LOL, we end up with 10 sub-arrays, each with LOL as the one element. Not what we want, but we want an empty array. So now we have 10 buckets, 10 slots inside of this one larger bucket called one array called digit buckets, and they're all empty. Now, we need to loop over every number, so this part's easy. Let's just do for let I equals 0, I is less than nums.length, I plus plus. So for each number, we're now going to take that individual number, which is nums I, and we're going to figure out at position k, so at index 0 of each number, what value do we get? And then k will change, of course. So we're going to do get digit of nums I, comma k. And so that will give us digit 3, 5, 7, 2, 5, the first time through. And then k will go up, and k will be 1. So then we'll look at this number, the index 1 number. And then I'll go up again, and we'll keep going. So we don't just want to get that number, we want to take that number that comes back, and then put nums I in the bucket at that index. So if I just print this out right now, that's going to be pretty ugly. But you'll see what we end up with. If we run our code, it's a lot of console logs. But the very first time through, we end up with 3, 5, 7, 2, 5. So 3, 5, 7, 2, 5, 2. So we need to take those numbers and put this number at index 3. This number we got 5, we need to put it at index 5. So we could just do this. We could do it in one ugly line, which I don't like. Digit buckets of that result. So digit buckets of index 3 or index 5, or whatever we get back, dot push nums I. Now this is kind of a gross line in my opinion. I'm going to break it up. But if we actually do this, and let's just do it one time, and then let's just print out the end of this loop, digit buckets. You'll see, well, I don't want to count my egg before they hatch, but everything should be in the correct spot. Like the first time through, we end up with all the numbers that have 2 as their first digit are in the 2 bucket. We have 23 in this bucket. We have these numbers that end with 5 in the 5 bucket. So that's all working. But I just don't like how long this line is. So I'm going to break this up a little bit and make a variable called digit. Just like this. Oops, copied one extra part. And then we'll do index of digit, push nums I. So we're going to get the digit. That will give us 3, and then this is just a way of breaking up the code. Digit buckets of 3 dot push number. Okay, so we're almost there, but the one thing we're missing is after we break them into their buckets, we need to recollect them into a new array and do the same thing. Otherwise, we're just keeping them in the same order and then just sorting them into buckets. So we're sorting them based off of their first number, and then we're doing the same thing based off of the second number, but we're never actually ending up with a new order to the main list called nums. So we need to, afterwards, right here, what we're printing out, after we put them in the correct buckets, we need to then concat the array. So there's a nice, easy way of doing this in JavaScript. We reassign nums to be array.concat, and then I'm going to use spread digit buckets. And I use the spread operator, the special syntax with 3 dots, which if you're not familiar with it, it allows me to pass in all the arguments or every element in digit buckets as an individual argument. And the reason I need to do this, rather than just passing in digit buckets, is if we imagine, and I'll do it down here, I do a dot concat, and let's say that I have 3 arrays, because this is an array of arrays, right? What we're looking at here. So let's say that digit buckets looks like this. It's very simple, but let's say it looks something like this. If I call array.concat, it's going to concat these into a new array, but they still are in separate buckets. If I want to take these numbers and just combine them back into the original form, so this, but in a different order, if I use the spread operator, the dot, 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 I end up with this, just the values there turned into a new array. So this is what I want. This is a nice, easy way. I don't have to manually, you could loop over digit buckets for each bucket, loop over all the values in that bucket, and push them into nums, or a new array. But this is a nice, succinct way of doing it. And that's all we need to do, aside from returning nums. So let's do that. And let's see if it works. What I would like to do here is do a console.log. Let's go with digit buckets here. And then afterwards, after we concat back into nums, console.log nums. Okay, let's run the code. Alright, so first time through, we end up with everything sorted, or not sorted, but everything put into the correct bucket based off of the 0 digit, the first one from the right. Then we concat this. So the order is preserved. Think of it as just smushing them all together into this array now. Nums looks like this. So we have 12, digit 2, followed by 9852, which ends in a 2, and then what ends in a 3 and a 5, and so on. So we took this order and just smashed it together. Then we went through and put them into buckets based off of this number. So you can see them here. So this is in slot 1, bucket 1. This is in bucket 2, bucket 4. And then we concat them again. So we keep this order, and we end up with this. So each time we get a little more sorted, then we do it again, and we look at the index 2, 0, 1, 2. So some of the numbers don't have a value there, in which case they're in the 0 bucket. So the smallest numbers are already in the correct bucket. But the 3 and 4 digit numbers are still working their way to their correct spots. So we concat again, we end up with this, and then one more time, put them in buckets based off of their index of 3 number, what digit is right here. And then we concat, we end up with this, we're done, and we return that. And that is radix sort. So I think it's kind of a fun one.